How's it going, YouTube? Dalton here. In this video, we're going to do number 2096, step-by-step directions from a binary tree to another. So you're given the root of a binary tree with n nodes. Each node is uniquely assigned a variable, or a value rather, from 1 to n. You're also given an integer start value representing the value of the start node s, and a different integer, dest value, representing the value of the destination node t. Find the shortest path starting from node S and ending at node T. Generate step-by-step directions of such path as a string consisting only of the uppercase letters L, R, and U, each letter indicating a specific direction. If we have L, it means to go to its left child node. So in this case, for example, what it would be is, if you were going down here, it would be left, right? And R means to go towards the right child node. So if you had, in this case, this would be R, right? And U means to go from a node, which is a node, to its parent node, right? So this is how you represent U. You're going from here to here. So we're asked to return the step-by-step directions of the shortest path from node S to node T. So here we have a couple examples here. You can see the root is 5, 1, 2, 3, null 6, 4, start value 3, destination value 6, as I pictured over here. You also have this one, which is just L, and we see here that the number of nodes in the tree is n. N is between 2 and negative 10.5. So what that means is we're never just going to have, say, like one node here. It's always going to be a minimum of 2 nodes, so that's very good to know. We don't have to deal with those edge cases there. You have the node value is between 1 and n. All values in the tree are unique. And we have start value and destination value are in the constraints of n. And the start value is not equal to the destination value, so they're always unique, right? So how would we approach this problem, right? Well, we had to split it up into a couple steps here, right? The first step is to determine where start nodes are, right? And then we had to determine where end nodes are, right? So then what we have to do is you have to get a path from start to end and keep track using letters. All right? So how do we do this? Well, what I'm thinking right now is I think a good first step would be to do a depth first search. As you can see in this example, we know that our start node is down here, right? So we need to do a depth first search because that makes a lot more sense than doing a breadth first search, where we take each of the lines here and go about to find the bottom. Since we know that we're going to the bottom probably, makes a little bit more sense to use a depth first search first. But we will have to use a breadth first search to find from the start node to the end node, right? Because simply a depth first search would be inefficient in this case. So how do we code up the solution? Let's do that. So what we need to do first is we need to define a variable in which we're going to call start node. And we're going to set that to none. And what the purpose of the start node is we want to save this, quote unquote, when we eventually find our start value here. Then we want to replace that with our start node, because we know that's how we're going to traverse the entire tree here. And we do the same thing with the end node. We want to store something in the dest value, right? Self.end node is equal to none. Another thing that we need to do is we need to keep track of exactly what the parent node is and what the actual node is, or the actual node that we're actually on is. So to explain that a little bit more clearly, let's just say that this was your root node. You would need to keep track of exactly what the parent node is. And the reason for that is we want to save this and we want to keep track of it as we're recursively going down the array, because we eventually need to go back up, right? Alright, so let's code up the DFS solution here. So DFS, I'm going to set the root node, and we're also going to set the parent node, right? So we'll take our base case. So if not root, we're just going to simply return, right? There's no really return value that's necessary here, so that's not entirely necessary. So we're going to set our parent. We're going to set root dot parent equals to the parent node, and we want to define the parent node, for example, if the root was over here, right? We take one look up, then this one's going to be the parents, right? Sorry for the ugly handwriting, but I hope that's clear, right? So now we recursively call the DFS function. So we go DFS, and we're going to go root.left, and we pass the root since the root is our parent now, and we go root DFS root.right, and pass in the root as our root is our parent, right? So now we need our condition when we're doing a DFS. So what's our condition? Well, we want to know when the start value has occurred, right? So if root.val is equal to start value, what we're going to do is we're going to set our start node, and we're going to have self there, self dot start node is equal to the root, right? And now we'll do the same thing with our end node. So self dot end node is equal to the root. All right. Now to close off the DFS, all we do is return, and we call our DFS using the root and none for our parent, right? So what have we accomplished here? Well, we found out exactly where our start node is, right? So instead of start node being a null value, we now have start node over here, and we have end node over here. So now all there's left to do is to, one, go and find a path from start node to end node, right? And secondly, keep track of the letters that we need to do in order to get to that destination. So what I'm going to do is I'm going to store two variables here. We're going to use a breadth first search to get there. I do believe it's the most efficient way to figure out our solution. And what we're going to do is we're going to have two different variables. So we're going to have a variable called node, and we're going to have a variable called letter. So what node's going to do is it's going to keep track of what node that we're on, and then the letter is obviously going to be the final output that we're going to have here. So it's going to be like UURL. This node would be keeping track, like we visited 3, we visited 1, we visited 5, we visited 2, and we visited 6. The purpose of this is to make sure that we don't visit any unnecessary nodes, that we're not like backtracking for no good odd reason, so that this letter won't get screwed up basically, right? So we use a breadth first search, so we add all our numbers to the queue, and then we just pop them, designate our node and our letter, and just keep going and we're also going to store it in a set in order to keep track of what nodes that we visited and also what nodes that we're on, right? So we'll typically have a set here in order to keep track of where the nodes are going, right? So let's do that. So the first thing we want to do when we're doing a breadth first search is we want to launch a queue, right? So what we want to do is we want to take our queue and we want to put our start node into the queue. Start node, and then we're just going to have a string value there, right? So we also have a variable called visited nodes, and this is going to keep track of what nodes that we visited, right? And what we're going to do is we're going to add the visited nodes into our set here, right? Self.start node.value, right? So it's going to add this 3 to our visited nodes. So let's write that down. All right. So what we're going to do is, now that we have most of it set up, now we're going to do our usual breadth first search. So while the queue is still valid, what we're going to do is we're going to start by popping our number from the queue. So if we had a queue here, what we have is 3. And then we pop that, and we're going to have node and letter queue.pop. So obviously one of our main conditions here is if node is equal to self.end node. Since we already found that out over here, what we're going to do is we're going to return the letter, right? Now there's a couple conditions that we need to do. We need to add all our nodes to the visited nodes so that we can keep track of where we're going, and we also want to add these stuff to the node and the letter variable as we're going on. So for example here, if we manually wanted to make this path, what we would do is we would have, say, this letter is obviously U here, this is U, this is right, and this is left, right? So as you're going up, you have 3 here, then 1, we store a U. Then we have 1 to 5, we store another U, right? We store 5 to 2, we have an R here, right? And then we have 2 to 6, we have a L here. So that's kind of how the code's working here. All right, so let's do that in code. So if node.parent exists and node.parent.val is not in visited nodes. So if it's not in the visited nodes set here, we're going to add it to the queue, and we're also going to add it to the set. So we're going to add it to the queue and add it to the set. So here's what we're going to do. Queue.append, right? Node.parent letter plus U, right? So here we're basically adding the parent to our queue here. So this would be like 1, for example, right? And then what we do is we have, say we add this to our letter, and this is going to be U, right? And lastly, what we need to do is we need to add it to our set so we keep track of exactly what nodes that we have visited, right? Visited nodes.add node.parent.val, right? So this is going to keep track of this, and this would be like equal to 3, for example, And what we're going to do is we're going to do the same thing with the left and the right. So here we have the left and node.left.val, not in visited node. And then we're going to have L, and then we add the node.left value. And obviously this is not going to be parent. It's going to be left. And lastly, we're going to do the same thing with the right. So right.val, not a visited node, right, and right. Whoops. Then this one is going to be R, right? So lastly, to end it off, we just return an empty string, because in this case you would ask your interviewer exactly what the default value here, but it doesn't really do a good job of explaining exactly if a solution exists. But that's something that if you were asked this question in an interview, I would make sure that you're making that clear. So this would be whatever the default return value is, and yeah, that should work. Visited nodes is not defined. Visit. Is that how you spell visited? I think so. And accepted, and submit. So we see that's a success. I mean, you could do better, but it's an O of n solution since you're going through it n times, as well as using O of n space complexity. So this is time complexity, space complexity, which is good enough in my book. So if you guys enjoyed the video, don't forget to hit like, comment, and subscribe. Leave me a comment telling me what you thought about it, and I'll see you next time.